So from now on, actually I have recorded previous lecture as well. But from now I will record the lecture and put it up to the Brightspace. I only updated like one section because I have the online and the Zoom session. So I'll double check. So from now you don't need to record it by yourself. I will record the lecture and post it to the Brightspace in the announcement. Okay. So for those of you who are want to review like any materials, you can do that. Just a reminder, okay, today midnight is project 1 is due. Hopefully everybody is already finish it or close to finish. Okay. If you're not, then yeah, you need to hurry up. So I think it's due midnight today. But you if you need help, you better ask for help during the day. Okay, don't wait until the last minute. Because if you last minute, if you have an issue with sales, nobody can help. Okay, everybody was particularly like a sales admin or the sales staff. They can. I mean, you can, if you really have emergency problem, you can call them during the day. Okay, during working hours, they can give you like a help right away. But if you wait until night, then that's gonna be too late. Okay, so that's about project number 1. Today we're going to continue about, so we're going to cover the 2 things. One is using the relational algebra, which is using MapReduce to implement this is a standard relational algebra. And then we're going to talk about how to use that to apply that to the matrix multiplication. So we talk about there are sort of like broadly 5 group of the relational algebras. One selection, projection, then union, intersection, difference. This is like one natural join and the grouping and the aggregation. So let's just explain them one by one. As I said last time, for database or for relation, the one thing is important thing is each row or each record is unique. Okay, there's no duplicate in the relation. So when you try to after you apply operation to your table or to the relation, then if it may result in duplicates, if that duplicate has to be removed. So that's this is one of the things we need to be careful when we apply the relational algebra. So the first one is selection. Selection basically is apply a condition C to each tuple, or each row in a relation, and produce as output only those tuples that satisfy C. Right. The result is the selection denoted as sigma. Right. Sigma. This is started with S. The sigma C on R. So you are applying the selection to the relation R with the condition C. This is basically is just try to selecting rows, right, to satisfy the relationship, satisfy the condition C. Since each row is already unique, then if you select in a subset of it, it's still going to be unique. So there's basically this is just to get in the subset of the rows. There's nothing really. This is very simple. Projection means for some subset S of the attributes relation produced from each tuple only the component for the attributes in S. So the resulting of this projection is noting as pi SR. Pi is for started with P, right? So that's a projection, right? So the P SR, this is S is a subset, and then the R is relation. So basically, so you're choosing columns. Now, when you're choosing columns, then it could be when you're choosing column, then now it may result in duplicates, right? So if you, in this case for the projection, when you're selecting the columns, if there's duplicates, then we need to we have to remove it from the relation. So this is a little bit different from the projection from the selection. For example, when you are doing a selection, say selection for this relation, right? For this relation, only the column 2, right? So the 2 column. Now you can see then the 2 column, if you left it out without any touch, it just has UR 2, 3, 3, 4. But this 3 is a duplicate, right? But then we have to remove one of them, become like a three rows and have 4 rows in this case. Union, intersection, and difference. This is the like a well-known set operations applied to the set of tuples in 2 relations. Now, this 2 relation has to be satisfied condition. They have to have the same schema. Okay, same schema means you have the same column names. So now there are also like a back version of the in the SQL with some more unintuitive definition. So we will not go to that. The union intersection difference is going to be the difference is like the intuitive definition of you have in mind. If you have 2 relation A and relation B with the same schema, that means the union. That means just you combine these two relations, and then if there's duplicate, you just remove them, right? So if they are the unique, you keep them. Intersection, that's just you just taking the ones. You say A minus B, right? A minus B. That means anything exists in the B, but anything exists in the A not B will be kept, right? So that's this is no, actually that's a difference. The intersection, that's A intersect the B. That means for the each rows or each the tuple, you have to be exist in both A and B in order to keep it, right? So that's intersection difference is what I described. It has to be only exist in one of the relation, but not the other one. Natural join is a little bit. Natural join is a little bit. You probably not everybody heard of this natural join. So this is, but the concept is pretty simple. That means it's given 2 relations, right? A and B. You have 2 relations, A and B. You compare each pair of tuples, one from each relation. So if the tuples agree on all the attributes that are common to the 2 schema, then you're going to produce a tuple that has component of each of attributes in either schema and agree with the 2 tuple on each attributes. Right? If the tuple disagree on one or more of the shared attributes, then produce nothing from the pair of tuples. So the natural join for the you have relation S and R and S, then define basically the R is a natural join with S. So what does it mean? Say you have a relation R, right? You have in the schema like A, B, C. So the schema is say just numbers, right? It's 1, 1, 1, 1, 0, 1, 1, 1, 0. Okay, so let's just make a made up example. Then you have a relation S. Okay, relation S and R, they don't have to necessarily has to be the same schema, but they should have some overlap. Okay, in order to join 2 tables, you have to have some overlap. Say the overlap is B and C. This has B, C, D. Okay. Now, in here, you may have, let's say this is a 1, 1, 2, 1, 1, 3. Then you may have this is having say 2, 4, 5, 3, 1, 6. Okay, so you have two relations. This relation R contains 3 rows, 3 records. Relation S contains 4 records. Let me just make sure. Let's see the stop sharing. So people can. Okay, so the people on the Zoom can hopefully can see that. So you have in this 2 relation RMS. Now, natural join, what you're going to do? You're going to compare each record, each tuple in the relation R, compared with each tuple within the in the relation S. So in this case, the comparison you're going to do is 3 times 4 equal to 12. Okay, you're going to do 12 comparisons, and then if when you compare if you do the comparison, if they agree, if the value on the shared attributes, if value they agree, okay, then you're going to produce a new tuple, which is going to join these two. For example, if you have row 1 and row 2, okay, they share, first of all, the shared attributes is B and C, right? So then since they agree, so this is BC and this BC, the same value, what you're gonna have is you're gonna have in this natural join, like this join, you're going to produce this A, B, C, D, right? You're going to produce a new relation with A, B, C, D. Now, the first one, the B, C, they are one, they are the same. And then you're going to have A is going to from R and 2 is from the S. So you're going to have this is 1, 1, 1, 2. This is a new tuple. Then the first row is going to compare with the second row in S. You see B, C, B, C, they also are the same. So then you're gonna join the first row and the second row, first row in R, the second row in the S. So you're gonna form a new one. Then first one and the third, B, C, they don't agree, they produce nothing. Then the fourth one, they don't agree, they produce nothing, right? So then you do the second row in the R. You can see the BC, they have nothing match with the BC in the second row in the R. So therefore they produce nothing. Then for the third row, you're going to have the same thing, right? You're going to have in the BC. BC is one. Oh, actually BC is 1, 0. It doesn't have anything. So then this does not produce anything as well. So just in case, if you have like a 1, 0, 7, like in this case, if you have in like 107, then this one gonna produce with this is generating this. You're gonna generate in 1107. You're gonna have a new record. So natural join, it depends on the shared attributes. Okay, if their value agrees, then you're gonna generating a new tuple in the joined relations. Okay, so it's a little bit complicated, but still it should be pretty simple once you understand it. All right, any question on the natural join? Okay. All right, so if we don't have a question, then we're going to continue. So the next one is for grouping and aggregation. So grouping and aggregation is should be pretty simple or easy to understand if you are familiar with in like the Python group by, right? If you know the group by and the aggregation, then this is exactly the same thing. Okay. So this is say you're given a relation R, you can partition its tuples according to a value on one set of attributes G. They're called grouping attributes. Then for each group, aggregate the value in the certain other attributes, right? So the normally a permitted aggregation are like a sum, count, average, minimum, maximum, with this is the opposite meanings, right? So we denote a grouping and aggregation operation for the relation R is by gamma x theta a R. So gamma means G, right? So this starting with G, so this means grouping. The gamma X is a grouping attribute, right? We are grouping on the X attributes. Theta A means we are going to apply the operation theta, which is to be for example, summation. This is the average, minimum, maximum, right? To the set of the attributes A for the operation. So the easy one would be when remember we talk about like say we want to calculating the female we have the grid, right? You have the class scores. You have grid 1, grid 2, grid 3, and you have gender, female, and their corresponding score. So if you want to see, I want to calculate the average score for each grid, right? So then the grid will be your grouping attributes, right? Score will be your the aggregation of the attributes we're going to apply the aggregation operation on, and the operation going to be average. So you're going to apply grouping on the grid and then apply the average to the score attributes, right? So this is a grouping and aggregation. So this is a very useful technique or a very useful operation in the database, or in the like data frame. If you're using Python, I mean, if you're using Python, this is a grouping aggregation is kind of like a almost like the basic operation you have to know. So these are the five basic the operations. Now let's see how can we use this to implement them with MapReduce. And then the next thing is so we're going to first to learn how to implement this is the basic operations, which is going to be very easy, and then we're going to apply this to the metric application. Okay, so they are by looking at itself is kind of like not that interesting, but when we apply this to the matrix multiplication, then I think it's going to become much more interesting and useful. So selection is for the map function is we're going to see for each tuple in the R. We remember we have a condition C, right? So for each tuple T in the R, we're going to test if it satisfies the condition C. C, for example, you have in the grid, like you have in this is the same score table, and you have in the grid, you have in the gender, you have the score, right? Grid could be you have in the so this is your record 1, 2, 3, 4 up to n. You have grid is 1, 2, 1, 2, 2, 3, 4. I have different grids and gender, male, female, male. And so I have score 90, 50, 100, 98, and so on. So your condition could be the grid equal to 2, right? It's just a filtering criteria. So or the gender is male, or the score is like bigger than or equal to 90, whatever. You can apply this is a condition C to this relation R. So for each tuple T in the R, we're gonna produce key value pairs T and T. So then the both key and value are T. We just I mean this is just you can just do T and 1. It doesn't really matter. We just need one copy of them. But it's just for the sake of the algorithm, we're just using T and T. So that reduce function is just identity, right? So you simply pass each key value to the output. So what in the map function is just simply just an if function. If this is tuple, you're gonna map is for each row, right? So if it satisfies C, you're gonna produce this key value pair T and T, right? So and then in the reduce function is just identity because you don't really need to do anything. Is each row is unique. So then the output exactly is so the output is not exactly relation because it has a key value pairs, but the relation can be obtained by just using the value component, right? So that's this is actually very simple. So this is selection. Projection is for each tuple T in R. You're gonna remember projection. We're gonna selecting some the attributes, right? So for each tuple T in R, we construct a new tuple T prime by eliminating from T those components whose attributes are not in the S, right? So you specify attribute set S, and you only pick those values. Now the output of the key value pairs is just become T prime. Now for this one, each tuple in R, you're going to generating a T prime. So in the reduce function, then for each key T prime, then you may have in several of them, right? You may have several because since you're only picking a subset. For example, in this example, if you have if you want to just pick in breed and gender, right? You can only pick up these two columns. Then after you do the projection, you're gonna have the score is gone. You can then for this one you're gonna generate one F. This is gonna generate two M. This is gonna be on F, right? So this is the key. The value is also one F. It's gonna be itself. Okay, two M is the one F. Now, when the reduce function, actually, this is all the t prime, right? This is also t prime. Now, for the one F, right? For the one F in the reduce function, the key, it actually can be having two of this is identical directly, right? So therefore, each t prime they may having a list of values which are identical values. Now, but since they only have a list of them, then what you just need to do is just turn this into in the reduce function, just turn it into t prime. Okay, so you're gonna produce the exactly one pair of t prime for this t prime. This is a projection. Basically, this step is remove duplicates, right? Remove duplicates. Now, the reason we're using this because for the map reduce, it has to come in with the key value pairs. You can use for the value, you can just attach one, right? You don't necessarily have to be t prime. You can just attach one. But it doesn't really. This is again just for the algorithm, the sake we use in the t prime, but you can if you just attach one as a value, that's perfect fine. So the reduce operation is just duplicate elimination. This operation is associative and commutative. So a combiner associated with each map task can eliminate whatever duplicates are produced locally. So the reduce task still need to eliminate two identical from the different task map task. This is just saying if you generating from the locally for the one map task, you can actually remove the duplicates first, right? Then but you can from a different map task and then the reduce function can be taken up by reduce function. This is just essentially just to save some communication time. Okay, so that's this is a projection. So these two are pretty simple. Okay, these are two are pretty simple. There's really nothing complicated there. Now the union intersection, this is kind of like the similar thing. For the union is we have two relation R and S for the A and B. So for the union intersection and the difference, these two has to be in the same. They have to be in the same. You have to have the same schema, right? So that means the attribute set has to be the same. Now, in the map function, okay, in the map function, turn each input into tuple T each input tuple T into a key value pairs T and T. Okay. Now, then you're gonna associate with each key T. There will be either one or two values. Then you just produce the output TP in the case. Now, union, you essentially just combine these two, right? But you want to remove the duplicates. So when you try to do the union, you don't really care if it comes from the first relation or second relation, right? So you can just put them together. Okay, you just put them together. So you just process each tuple from either of this relation. So what you're going to generate is you have a T and T from there. So you can only have two cases, right? You can only have two cases. That means if you have a tuple from only unique in R or unique in S, then this tuple you only have one copy, right? Because each tuple is unique, so you only have one copy. Or if this tuple appear in both relations, you're gonna have two copies. Right? You're gonna have two copies, which is you're gonna have in this is you have 111 in this and 111 in this, so you're gonna have two copies. So in the reduce function, you're gonna either having this is T and T, or you having this is you have second case, you have this case, right? You only have these two cases. So reduce function is no matter what, you just turn this into TMT, this tuple, and then combine them. Okay, so this is the union. Intersection is the same thing. Intersection, you don't want to intersection also you don't really care which one is come from, because if only intersection is if it's unique in one of the in R or unique in S, that means you only have one copy. If it has two copies, then that means it exists in both in both relations. So that's the one you want to keep. So then in the reduce function, so for the union, you're going to keep the both. In both cases, you're going to keep it and generate a TT for the union. For the intersection, then if you only have one value, then this goes not produce nothing. Then if your list has two copies, then you produce a TMT, which is going to be your intersection, right? So this is given. You have this is given that each tuple in the relation is unique, and you want to do the union and intersection. You can just by checking in the reduce step, okay, in the reduce function, you can check in like the list attached to the key, how many number of values attached to it, right? So if it's two, then that's intersection, right? So this is pretty simple. And question on the union and intersection, is this clear? Yes. Good so far. Yeah. Okay. Because this is if you are talking about key values, this is sometimes it could be a little bit confusing. Okay, this is but you for example, why this is a TT, why this has some two copies there are. This is because when you generating this is for the mapper, you generate key value from each one of them. You either generating, if it's unique in one of this relation, you're generating you only have one value. If it's common in both, then you're gonna have two values, right? Because you're gonna have one copy from the first relation, another copy from second relation. That's why you have a intersection. So yeah.
For like these are all processed on the parallel, right?
Yeah.
So after the user is operated, you also have to check if each outcome the user have the same value.
You don't need to check again because this key is already unique. The key is unique.
What about like what reducer one has?
No, you only have one. You only have reducer gonna collect all the key, same key. You're gonna go to the same reducer, right? That's where this come from. So each reduce function they only produce process one key. You have a question?
Yeah, I might be moving in, but it's kind of a little physical stuff. Once the reducer has this, it's just stored to a single file, and then it's whenever it's called, like that specific subfile will go.
Yeah. So once a reducer, what you're gonna do is the reducer gonna save it to the distributed file system, right? And then you should have another function like to reading. This is auto from reducer and try to summarize. Like for the project, say you're gonna have a reducer. Say you have 40 reducer. For the reducer one is gonna produce a number from 1 to 25, right? So then after this, you're gonna have a file. This is having one. This is number. And this is the frequency. You're gonna have one, say you have 100, two, you have 300. You're gonna have this numbers in one file. Then reducer 2 is gonna 25 to 50. You're gonna generate in the same given file, right? Now you will need a program to reading all this together and then sort them, find the highest frequency, right? So you need after the reducer, you need this typically can be done using the master node. Okay, again, since we haven't really talked about that yet, in the project, you probably need another program to summarize to find the highest frequency. Like seen in here is after you have produced the TNT, you need one program to convert it into a relation. Okay, so that's but in here, the job that, because that job is very simple, right? That job is easy. So we just assume it can be done without any problem. Okay, so this is a okay, sorry. Because there's something there's someone working in my home right now, so they're trying to ask me questions. I just need to check in the message to make sure there's nothing went wrong. Okay, so then the next one is the difference. Okay, so for the difference in the operation, now for the union and the intersection, it doesn't really matter, right? So this is it doesn't matter is R union S or the S union R intersection S or S intersection X is going to give the same result, right? So that's why in the union intersection in the materials we don't really care is the tuple, like in the map case, is coming from R from S. It doesn't really matter. Okay. Now, but for the difference, now you will have then it's different, right? Because R minus S and R minus S and S minus R, they represent different things. So for the C, let's see, we want to do the one of them. So for the map part is you're gonna now for the each tuple, okay, they're gonna attach the R, the name of the R, the relation, name of relation to each tuple, just to make sure you know where it come from. So for T in the R, you're gonna produce a key value pairs with T and R. So this R is just a name, okay? It's just a name of the relation. It's not the whole table, okay? It's just a name. So make sure that's this. So the value is actually very small. Then for tuple T in the S, you're gonna produce a key value pair TS, right? Now note that this is the intent is that the value is the name of ours, not the entire relation, okay? The entire relation is gonna be huge. In the reduced part, so for each key T, okay? Now for each key T, in the reduced part, you only can have in three things, the three possibilities. So if this T is unique in R, okay, if this tuple is unique in the relation R, then it's nothing in S. In the reducer, its input is just TR, okay? So if it's unique in the S, then in the input for the reducer, it's going to TS, okay? So if it's common in both, then in the input after you do the sorting and aggregation, the input for the reducer is going to be R and S. So you're going to have two values. Okay, you're going to have two values. So if you are doing the if you're doing the if the associated value is R, then we're going to produce TD. So if we're doing the R minus S, okay, if I do R minus S, what you're going to essentially do is you want to only keep those values which are unique in R, right? So we're going to remove the duplicates, remove the common tuples, the couples existing in both S. So therefore, if for R minus, so if we want to do R minus S, then we're going to do is this one, we're going to convert into T and T. For the second, we're going to do nothing. For this one, we're going to do nothing. Because this means this tuple is from relation S, we don't want it. This tuple exists in both R and S, we don't want it. We only want this tuples with unique in R, right? So this is how difference is done by attaching a name to them. Now, if you want to do S minus R, then what you're going to do is going to keep T at S, and you get rid of TR and TRS, right? You get rid of that. So this is by attaching the relation names to tuple, you can making this a difference. Okay, so that's by again you only have this is three scenarios, right? Three scenarios when you generate input for the reducer. Natural join. Natural join is a little bit I mean, to explain it is kind of hard, but to really to implement it actually is not hard. Now, for each tuple, now we have to break it into two components. Okay, one component is a common is a component with a common schema, and one is a unique schema to the relation, right? So, for example, if for each tuple in the R, we can break it into the A, B. A is the attributes, the value of the attributes is only unique to the R. Okay, the only unique to R. B will be the common values, like in so this is, let's say B, C, D. Okay. Then for each tuple R in here, we're gonna produce a key value with B. B will be the common schema as this key, and then you're gonna have R in the value component. You're gonna have in two components, right? You have R is a relation which relation come from. A is will be the rest of values. Then for each tuple in S, you're gonna have B and C. B is will be the common one, so then the produce key value will be the key will be B, and the S and the C. C is the value unique to C. So in this case, for example, like give example. Then for the relation R, for this one, you're going to generate the key value pairs is going to be 1 and 1 because the common schema, common attribute is going to be B and C, right? Then the key will be 1 and 1. The common schema for the first row in R is going to be 1 and 1. The value is going to be R and 1, right? Because this is the A is this will be the A. So then the second one, this is going to generate 1, 0. This is going to R 1, and the third one is going to be 0 to 1. 0, 1. It's going to be 1 and 0. This will be the key. The value is going to be R and 1 as well. All right. So in the R, you're going to generate in three tuples, or the 3 key value pairs. For the S, you're going to have in the BC, you're going to be 1 and 1. You're going to have in the S and 2. Then this is going to be 1 and 1. This is your key, S and 1. This is going to be generating 2 and 4 is your key, S and 5. Let me just walk through this one so we can see. Then you can have S and 6. Last one is 1 and 0 as a key. Then as S and 7 is your value, right? So for each one of them, you're gonna generating the key value pairs. So the key will be the common the values, which is always the common attributes. Once you have this, then in the reducer component, you're gonna have in this is for the key 1 1. Okay, so this is input for the reducer is gonna have in 1 1. This will be your key, and the value is gonna be a list, right? The list is gonna be R1. So this is one key from here. On this side, you're gonna have in S of 2, S of 1. Right? For the key 1 1, this will be the one of them, right? Now for the key, you're gonna have another key for the 0 1. So key of 0 and 1, you're only having the value from R. So this is gonna be just R and 1. It's just one key, one value. Right? So and so on. So until you're gonna have in for the key of 0 1 is actually unique, right? So key of 2 4 is also unique. Key of 3 1 is not unique. So until you have the key of this is a 1 and 0, then it's gonna have the value. It's gonna have R and 1 and S and 7. You have 2 values. Okay. So the input of this is for the reducer is going to be given like this. So what I'm gonna reduce is gonna do is gonna scan the list, associated list, okay, associated list. In the list, you're gonna have in R and S, right? You're gonna have R and S. So you can break them into two groups, right? One is component is from R, another is from S. So in the reducer, what you're gonna do is for each value of R, you're gonna match with all the value of S, right? So you're gonna have you can have like a for loop. So R the value you have 1, the S has 2. So you're gonna for each value in the R, and you're gonna match with the value in S, right? With S name. So then this is gonna generate in two relations. So this is gonna generate one, which is from R. This is only unique to the R. Then common value 1, 1. And then it's 2, right? So then you're going to generate in the first tuple, and the second tuple will also be 1, 1, 1, and 1. Okay, so that's the this is from the first. This one you're going to join, giving you this is a 2 tuple, and if this is attached, if the value attached to one key only having a component, only have the value from one of the relation. There's nothing, right? In this case, only has R, there are no S, then we can ignore it because nothing to join. Okay, nothing to join for this two. So for the last one, what you're gonna have here, basically have 1, 1, 0, and 7, right? That's how they join together. Card and period using one slope, but not using multi-process library. Okay, so this is there was a question in the chat asking I have used one Slurm file but not using multi-process library or Python. And use no MPI concept, could you please? So I already said that if you're using the, I didn't cover MPI in the class, so I didn't really expect anybody to use MPI. But if you know how to use them, that's fine. It's your choice, but just make sure you use it right, okay? Because if you do it wrong, you are not going to get a full credit. Okay, so this is a natural drawing. Basically, this is in the reduce function. This is I'll just read it so you can match with the procedure with the data on the whiteboard. So each key value B will be associated with the list of pairs that are either from R or S, right? Then we construct all pairs consist of one with the first component R and the other one with the first component S. So therefore, you have in this RA and SC. So the output will be B A1, B, C1, and so this is going to be having this is right. You're having the B, you're having A1, B, C1, A2, B, C1, and so on. So therefore, B is that is B associated with the list of tuple that can be formed with the R tuple and S tuple with the common value B. This is just the things we just talked in this class. Just talking on the whiteboard. Okay, so any questions on natural drawing? Is this clear? Okay, so we're actually gonna use the natural drawing. Okay, we're gonna use the concept because matrix multiplication essentially is natural drawing followed by grouping aggregation. Okay, so this is the natural drawing. Although the concept is not that, it's kind of weird, not really weird, but it's a little bit complicated. But this is a useful concept. We're gonna actually use it in just a second. Okay, so make sure if you're confused by the procedure, you can ask now. Otherwise, we're gonna build up on it. Then that's you can make it a little bit harder. Okay. All right. So grouping and aggregation by MapReduce. This is a grouping aggregation again. This should be pretty simple. Now then, grouping aggregation is an operation on one relations. So we're gonna break the attributes into three components, A, B, C, right? So A is a attribute we're going to use for grouping, right? Like the grid, right? In there. B is attributes we're going to apply the operation theta, right? We're going to apply the operation onto it. So if you want to take an average of the score, average of the height, right? So this is B is your operation is going to be on. C in this case are the rest attribute, which we don't have. We don't. It's not in the grouping attributes or the operation attributes. So again, this is the notation. We're gonna do the grouping on. We're gonna group on A and apply the operation theta to B. Okay, for the relation R. So for the map function, then for each tuple A, B, C, we're gonna produce a key value A, B because the C is not using anyway in here. So we just do the A and B. Now for each key represent a group, right? So now each key is represent a group. Apply the aggregate operator theta to the list of the B values associated with a test key for key A, right? Because then the list is B1, B2, other Bn. These are B values associated with the key A. So the output is a pair of AX, where X are the results of the applying the theta to the list, right? So if the theta is sum, they just sum it up. If theta is max, you just take the maximum. So the grouping integration is actually very natural for the MapReduce, right? For the MapReduce component, because then in the map part is you separate out the key. In the reduce part, well, you apply the operation to the value you want to apply the operation. So this is the grouping integration. I mean, it's extremely natural with the MapReduce. Okay, so this is the five the basic relation algebras and how do they implement within the US MapReduce. So any question before we move on to the matrix part? Good. All right. Now let's see how can we using this is concept to work on like a more interesting problem like matrix multiplication. So first of all, the matrix actually can be expressed as relations. Okay, so we can think of a matrix as a relation with three attributes: the row number I, the column number J, and the value of the row column. Right. So then they associate. So therefore, we can view the matrix M of the relation M, which is I is a row number, J is a column number, and V is a value. So each input of this one is actually three values, right? So with tuple ij, mij, and we can view this matrix N is another relation, which is JKW, right? Is JKW. So with tuples JK and NJK. Why do you want to do that? Because if your matrix is very large, okay, say you have like 1 million by 1 million matrix, very likely your matrix is gonna be sparse. Okay, it's not gonna be dense matrix. Sparse matrix means your matrix, most of the entries are just zeros. Okay, most entries are just zeros or NAs. You don't have value in there. So only a few of them could be the has values. So since we can omit like tuples for matrix elements that are zeros, then this relation representation is often a good one for a large sparse matrix. Okay, so we tend to have, if we want to store a matrix, let's see, if you have a matrix, right? You have a matrix, it's 1, 2, 3, 4, 1, 2, 3, 4. This is having like a M11, M12, M13, M14, and so on. So you have this values. So you can think of how do you gonna store the matrix? So the matrix can be stored in a way you can store as just as this is as a matrix in the text file, right? As a text file or whatever the some like binary file, you can just store them as a matrix. Use the coordinates, which is actually can be you don't really need these coordinates for the I and j, right? You can just embed this is the I j into the how data is organized. Okay, so in these cases, okay, so you see you having it's a m by n. This is a let's see, capital I by j matrix. Then you will need I times j times whatever how many you need for one number. Say your float you may use like a is like a two. Say it's an integer. This is using like the 2 bits or what typically using this 8 bytes. So this how much space you're gonna take in on the disk or on the RAM, right? So you're gonna take in this. So when the I and j are large, say this is a million by a million. This is actually taking this is a huge space, right? It's a huge space. But this is dense. This is for if your matrix is dense. Dense means every entry or most entry has values. Then you have no choice, right? You have no choice. You have to store in that way. Now suppose if this is a million by million matrix, you only have say 0.1% of matrix of entries has value, okay, or even less, okay, even less, or even having like a 0.01% of the has values. Then if you still using this the way to store the dense matrix to store this is a sparse matrix, it's kind of a lot of waste, right? It's a lot of waste. So instead, then we can basically convert them by using this is using like a specifically specify out their coordinates, right? The ith row jth column and its value. So now for each entry, its value gonna be double, about triple, right? You're gonna need like 3 times for each entry compared to the dense matrix. But now since you're only having this much, so essentially even multiply 3, that's like even you multiply this by 3, then that's still 0.03% of your original space, right? That's a huge saving. Okay, that's a huge saving. When I say 0.1%, 0.1, that's even in reality that could be even less than that. Okay, even less than that. I can the example I can show you is so if you want to representing the website like if you want to do the PageRank, right? So first, if you want to do PageRank, then first thing you have to represent the relation between website for each website. Now, suppose you're using the metrics to representing the how website how they connect to each other, right? So if you say if you're having URL1, if you have website, if it contains a link, okay, to another one to another website, then in the matrix you're gonna have in like a value 1, right, to represent their link, right? So 1 is pointing to other one. Now, say if it's having a 1.2, you're gonna have a 1 in here. If you don't point to that, you're gonna have a 0, right? You're gonna have a 0. So this is point to 1. From 2, you can point back. You can have 0, 0, or you can point to 4. 3, you don't point to 1. You can point to 2 and 0. 0 doesn't point to anything. For 4, you can point to 0, 0, 1, 0. So this is basically in this metric saying I have website. You can point to the second website and the fourth one. For the second one, you can point to 1 and 4, 3 just to point 2, 4 just point to 3, and so on, right? So you can use that. Now think about if you're having by the way, do you guys know how many like roughly how many what's the total number of the not counting the dark web, right? So just the website you can access. So what's the number of like websites or the pages or the web pages out there roughly? Like, do you guys have an idea like how many web pages out there in the? Yeah, but on the counts like roughly. Is like in millions, in 100 millions, in billions, or in hundreds billions, or which scale you guys think it's gonna be? Yeah, roughly it's about like 4 billion web pages. Okay, it has been constant. It has been some web pages generally new, some web pages is gonna be like retired. Now it's kind of reached to the stable status, about 4 billion web pages. So that means if you want to study the relation of the web pages, you actually have you need to working with 4 billion by 4 billion metrics, right? If you want to represent the relationship for the website. I mean, 4 billion by 4 billion, that's a huge metric, okay? You cannot even think about it. But on average, okay, how many links you can think on average, how many links you're gonna generate from like one website point to other website, or how many links a website you can think from website one, how many links is gonna coming from the website to point to other one? It's like a single digits, double digits, I mean thousands on average, or millions. What kind of level you guys think it's gonna be? Yeah, you can include ad links. I don't think that matter that much. I would say, I mean, it probably not in millions, right? It's not possible like for one website, you can, on average, okay, I'm talking on average, you can contain millions of links out there. Thousands probably is already a stretch, right? I mean, it's probably like a 50 to 100. That's already a lot. Okay, so on average, every web page has like 50 or 100 outlinks. That's a lot. That's actually a lot. So let's see 100. Okay. Let's see that your this is your web page is 1 billion. So each link contains 100 outlinks. So in this matrix, you are talking about hundreds over 10 to the 9, which is 1 out of 10, 7. This much entries. Okay, so this matrix is billion by billion, but there's only this much. Okay, there's only this much has entries into it. Okay, so it's 1 out of 10 to the 7. That is 0.0000001% of matrix has value. Okay, so this is an extreme sparse matrix. You can visualize, right? So in this case, by represent, if you're using the traditional dense matrix way to store those everything in there, that's just not feasible. But if you're using this is relation, the concept, okay, to store the coordinates and the values, then it's much efficient. Okay, I would say much efficient to do that. So so using the relation to express the large sparse matrix is actually a very common way. I mean, is a very economic way to do that. So so it's possible that IJK are implicit in the matrix of the element in the file represented by rather than explicitly with the element itself. That's what you're saying. This is for dense matrix. For sparse matrix, using relation. I hope that by now I convince you guys for sparse matrix using this as a relation to represent them is a good way to do that. Okay. Now the question is, if you express the matrix into this is if you express the matrix in this relation format, now how can you do the matrix multiplication? Right? We know the matrix multiplication essentially is so you have a matrix M, which is I by J the dimension. If you want to multiply with another matrix J or N with the J by K dimension, this is going to produce it's gonna produce a multiplication and with an I by K matrix, right? So with this with the elements in here, P, J, K will be a summation over J over Mij and Njk, right? So this is a formulation for matrix. So if you have the matrix, the square, right? So the matrix this is square. You know, this is I by J matrix. This is M, and then this is the J by this is the J by K matrix. This is for the N. So if you merge them together, you're gonna have a matrix. This is I by K, and then right. This is how it looks like. I mean, each entry of this is elements in the multiplication will be summation of the Mij or on each of this. So each column, each row of the I going to multiply each column of the N, and then they produce the corresponding component in the multiplication, right? So that's this is the product. So it turns out, okay, this product or the matrix multiplication is almost a natural join, okay, followed by the grouping aggregation. That is the natural join. We're going to apply the natural join of this is the M relation, which is a matrix, right? With IJV, with another matrix N with JKW. Then they only having actually J in common because that's J is column. J is the column in the matrix M, and J is the row number in the column N. This is because this is where we're gonna fin on operation, right? So then they have J in common would produce a tuple IJKVW from each tuple of IJV in M and tuple JKW in N. So this would be the natural join. Natural join, that means if you're having this is J in common, we're gonna associate with in every single one of them. Okay, every single one of them in the M and every single one in the N, they produce a natural join. So this 5-component tuple represent the pair of the matrix elements you're gonna have in Mij and Njk. Okay, so this is right. So what do we want instead is the product of this element. That is the four component, which is the tuple is IJK VW. VW, this is they can be multiplied together because that represents the product of IJ times NJK. So once we have this relation as a result of one map reduce operation, the next step we're going to do the grouping and aggregation, right? We're using IK as a grouping attribute because that's where we want to produce. And then we're going to apply sum of the VW value on the over J, right? Over J. So then we implement this as the matrix multiplication is actually as a cascade of 2 map reduce operations, right? So one map reduce going to do the natural join. Natural join is going to join the ones which is they have in the common J together, and then the grouping aggregation is gonna produce this is you're gonna sum up these two things. Okay, sum up these two things. Is this clear? I would be very surprised, okay, if you guys can get this in the first pass. It's not actually confusing, okay? It's pretty confusing. You have to think a little bit. It's not that the 3, 4. Okay, so what it does, okay? So basically what it does is so I'm trying to think of a way to okay, anyway. So what it does is you try to join the everything in you have if you have a record, okay, you have. So remember, so this is an M matrix, okay? M matrix. I'm just use a simple example, okay? So let's say this is a 1 0 0. This is a 0 1 1 1 0 1. Okay. Now for the M matrix, so what you're gonna have is so you're gonna have in the relation, if you convert the relation, so for the M, what you're gonna have is 1 1 1. Okay. First, this is I J, the value, right? Then the value is gonna be 2 2 1. Then 2 3 1, and then you have 3 1 1, 3 3 1. Okay. So this would be the this value. I mean, this is and the last one is the value, right? So I just choose the one for simplicity. Now for the matrix n you could have in just say it has to be 3, right? Let's just do a 3 by 2 matrix. Okay. Let's say this is a 1 1 0 0 1 1. Okay. Now for the matrix n, what you're gonna have is it's gonna have 1 1 1 2 1 1 2 2 1 and 3 2 1. Right? This is a then when you represent the n is gonna be this. Now this is I J M, this is J K and W, right? So this is this is attributes. This is the attribute I J M is J K W. So you have in the common one is J. Now for them to join, okay, for them to join, they have to see for the J, they have to be the same. Okay. So for the J to be the same, that's basically is you have in this J, you want to join is for this J, you're gonna have this is so this J and this J, they are the same, so they're going to be joined together. So when they join, okay, that means there is a possibility for these two values to be multiplied together. Okay, there's a possibility for these two. If they don't have the common J, okay, if they don't have the common J, then that means the NW, they may not be multiplied together. Okay, they may not be multiplied together. So if you have this one, so when you do the matrix multiplication, so this one and this one they can multiply together. This one and this one they are not going to be multiplied together, right? Because the J in this one there's no entry. There's only having this you have in the this one you're gonna have in the entry for the J is gonna be 2, but you don't have the one in here, so there's no multiplication. Okay, it's not gonna happen. So the J control, basically J is trying to pull the values. They can be multiplied. They have the possibility to multiply together. Then put them into one tuple. Okay, so then that's what it's about. Okay, so just if you're still confused, just to walk through this example a little bit, you're going to see exactly what this does. By doing this lateral join and then followed by grouping aggregation, we can do the matrix multiplication, right? By using this tool. So therefore, we can basically we can generate two MapReduce jobs. Okay. So the first job is you're going to have in this map function. Map function is you're going to produce for the matrix value Mij, you're going to produce a key value J associated with Mi and Mij, right? This is what M here is relation name, right? So J is what the common attributes. Then for the matrix N, we're going to do the J, Nk, and Njk. In the reducer function, for each J, we're going to examine its list of associated values. For each value comes from M, okay, and each value comes from N. Then we're going to produce the tuple I, K, M, mij njk. Now note that this is the output of reduced function is a key. It has a j key associated with that. So therefore, we can produce is actually j is having attached of this set of values. We have I1 K1 V1 I2 K2 V2 and so on. So you may have p values. Okay, you have p values attached to the j, and each one of this value is gonna be corresponding to I and k. So in this case, we're going to produce. Then we can use that to produce the value of ijk and vp from this. This is the output from the reducer. First map reduce job. But the second reduce job, actually not so fast. This is actually the one in the second map task. So in the map function in the second map reduce job, what you're going to do is going to for the breakup, okay, for the key j, and it has a bunch of values associated. You break them into this key value pairs, which is having this is the I1 K1 and the V1. Because for now remember for the second cases, the j is not important anymore. Because the j is not important because we don't need for the mappers output from the second job, we don't need j anymore because j is going to be associated with each value, each tuple. Because later on we're going to sum up over ik, I1 and K1 is already sum up over j already, right? So therefore we don't need for the key value pairs out of this is for this map job we don't need j anymore. So the reduce function basically is just for each key ik we're gonna sum up all these value associated with this key. And then that'll be the matrix, the p value in the matrix multiplication. So this is it's a little bit I think if this is the first time you see it, okay, there are going to be a little bit reading to that, you're thinking to that. Because you want to fully understand it, you have to the best way to do it would be work out the example. Okay, that is going to give you the best way to do that. Now, this matrix multiplication actually can be done in one step. Okay, be done in one step. The ones we see here is we kind of like using two map reduce jobs, right? One is doing the natural join. The second one is doing the grouping aggregation. So these two things put together is a matrix multiplication. Now, but we know map reduce is kind of slow. Okay, it's kind of slow. We have to use we kind of have to use the we have to each time it's the input and output is from hard disk, so it's slow. So if we can make this is a two map reduce job, condense them into one map reduce job, okay? Then that's going to be really speed up your task. This actually is doable, okay? This is actually doable. We can actually do this into one shot. So I will just go through the algorithm today and I will explain why it works, okay? In probably next time. So what you can do is this. In the map function, okay, for each element mij in your matrix on, we're going to produce the key value pairs ik, mj, and mij. So for each value mik, so like in this case, okay, if I have a value of 1, 1, m, now from here I'm going to actually going to generate three values. Okay, each one of them I'm going to generating k copies of them. Okay, k copies of them. So from this one, what I'm going to generate is 1, 1. This will be the ik, right? So we're going to have you have m. So m is the name of it. J is 1, and the value is 1. Okay. So I'm going to generate this guy. I'm going to also generate another key value is 1 and 2. Going to have m
1, 1. So what it does is basically is for each value in this M matrix, I duplicate it k times. Okay, I duplicate k times. This is to duplicate times is just to make sure when we later on when we try to do the summation, I have value to sum up. Okay, so for each element M in there, we're going to produce the key value pairs ik and mij. Basically, is duplicate each one of them k times. Now, for each element njk in the N matrix, okay, we're going to produce a key value ik, the same thing is ik, right? For up to I times, okay. So I'm going to duplicate each value in here is 3 times or I times in this case in this example. So what you're going to have here for this value, okay, so this value, what you're going to generating is 1, 1, 2, 1, 3, 1. So this is going to be the 3 keys. The values is going to be n 1, 1, n 1, 1, n 1, 1. Okay. So you can see what it does is duplicate this is the elements in the M k times, duplicates each elements in the N matrix I times, okay, by generating like multiple copies. So you can have in this is ik as example. Then for each ik, key is not is ik, okay, you can have associate list with mj, mij, nj, njk for all the possible value of j. Now the reduce function, what you're going to do is going to connecting 2 values on the list that have the same j. So if for this ik, if they have the same j, say the j equal to 1, okay, same 1, then if you have the same j, then you can do the multiplication and sum it up. If they don't have matching j, then those values are going to be ignored. So therefore, the j's value on each list must have the third component mij be extracted to be extracted and multiplied. So then this produce or sum up giving the value of this is a matrix multiplication. So in this, if you do it in one step, it's kind of like you using the you generating a lot of like redundant copies. These copies, many of them actually not going to be used. Okay, it's actually not going to be used. I actually have a graph. Okay, I'll show you next time. Then the graph is going to help you understand this is like a matrix multiplication in one step, much easier. But now the time is up. So we're gonna stop here. But any question or anything? Okay, so we'll go back review this matrix multiplication a little bit. Okay, so then the next time I'm gonna give you guys a little bit more intuition about why it works. All right, that's all for today.